Welcome everyone to AP Physics. This is going to be our first topic of the year. We're going to be starting in Chapter 3, which deals with the mathematical quantity called a vector. We'll get into that in just a little bit, but what I'm going to be doing with you guys today is giving you some background information on numbers in general. Now, I'm not going to take you all the way back to preschool and go through all the basics. I'm assuming that we can just pick up where I think you would have left off in some of your math classes, but again, this is just going to give you some background information on the types of numbers that physicists typically deal with, and then we're going to be getting into Chapter 3. So first thing I want to mention is I'd like you either to pause the video in a moment or do it after watching this video, but I'd like you guys to go to YouTube, and what I want you guys to do is watch a video. The video is called The Map of Mathematics. So it deals with all the different areas of math, and you'll see that over the course of the year that us as physicists, we make use of all the different types of math that exist to solve various problems about the physical world. It also gives you a little bit of history of some math, which some of it we're going to go over today. But it's 11 minutes long. It's well worth the watch. Anybody interested in math will enjoy hearing about some of the different topics, and see how many of those areas seem familiar and how much seems very far-fetched or odd to you. You'll find that there's a lot more to math than what you guys have covered so far in your educational experience. So for us, we're going to be talking about two different types of numbers. The first of which are known as scalars. And if there's anything you guys know, it would be the math behind scalar quantities. You guys should be experts in that because these are the typical numbers that you're used to dealing with. And we would describe them as having magnitude only. Magnitude is a word that's used to describe the amount of something. So we use numbers to represent quantities in nature, typically measurements that we're interested in making to describe certain aspects or characteristics of an object or a system. So scalars are going to be those quantities that we're going to be using to represent how much of that measurement we're talking about. But the other type of number that we're going to be working with are vectors. And we had a basic introduction last year to vectors, but it's going to require us to go a lot deeper into the math behind vectors, which some of it is familiar, some of it is completely new. But it's going to be important for us in order to generalize a lot of the mathematical tricks that we do to solve problems, to look at more complicated situations. Vectors are tools that should hopefully seem helpful in solving certain types of complex problems. But what a vector quantity is something that has both magnitude and direction. So certain quantities will naturally just go into one of these two groups. For instance, if you're talking about mass, mass would be an example of a scalar quantity. Because it tells you the amount of matter in an object, but does not require that you describe what the direction of that quantity is. So there's no need to say the object has a mass of 5 kilograms north or 10 kilograms south. It doesn't really make much sense to describe it in that way, and so naturally mass falls into a scalar category. For some other examples of scalars, we have measurements of pure length. If you're just looking at the dimensions of an object, so we could also say distance, and since measuring lengths of objects can help you to determine such quantities as area and volume, then these would all fit under the category of scalars. So if I'm measuring the length of the side of a box, I don't care what side it is necessarily if I'm just looking to find the volume of the box. So that goes to show that if we do not care about a particular direction, then we're dealing with a scalar. For some other examples, we have time, speed. This would be the measurement made by your speedometer. So especially when we talk about motion, direction is going to be an important quantity to talk about. But if I simply say that the car is moving at 50 miles an hour, it could be moving 50 miles an hour in any given direction, but unless explicitly given, you wouldn't know, based on just given the detail that the car is moving 50 miles an hour. So that information alone cannot give you direction, so that means speed itself is just a scalar quantity. Some other quantities that we've encountered at some point would be energy. Doesn't have a direction. Neither does work. And some quantities that we may not have covered or you've seen in the past are quantities such as power, temperature, density. These all fit the classification of scalars. One way of representing scalars is the use of a number line. So on a number line, we can represent scalars using points. And because we're not worried about a direction, these points don't depend on any sort of coordinate system. So looking at this number line, you sort of get a history of how numbers were developed over time. So the first numbers that would have been thought of are what are commonly referred to as the counting numbers, which are the integers, and specifically positive integers, because if you have, for instance, a basket of apples, you pull one apple at a time, you're counting whole numbers of apples. So if you want to describe the number of apples in your basket, you're counting one apple at a time, so you're going to need single digits, which represent the amount of apples that you have. So again, that would be a scalar quantity, and we're using these whole number integers that are positive in nature. So it would also then be later that the number 0 and the concept of 0 was invented. So we're going to place 0 at the center of our number line, and then place some strikes to represent the various values of integers. And so I can label them 1, 2, 3, 4. And if I have 1 apple, then I can place a dot at 1. If I have 2 apples, I can shift that dot and place it on 2. Now, the concept of taking amounts away from something also was thought of. So, being in debt, you owe someone 2 apples, all right, could then be a way of thinking about where negative numbers come from. So you have no apples to count at this point, so there's no apples in my basket, but I'm keeping now track of how many apples I owe to someone else. So again, the positive integers here are representing things that I can count. The negative integers would represent quantities that I don't have, but still need to keep track of. And so these quantities, these integers would extend on forever. But now, what if someone took a bite out of an apple? Then if these integers represent whole apples, you're going to run into a problem with placing a dot directly on one of these strikes. So let's say you pulled out 2 apples and then half of an apple. Where would you place the dot? Well, depending on how much of that apple was bitten into, you might place that dot somewhere in between 2 and 3. So the space between 2 and 3 must be occupied by other numbers as well. And so any number that can be written as a fraction of the integers are referred to as rational numbers. Now, believe it or not every number on the number line can be written as a fraction of the integers. So think of zooming in to the space between these whole integers. You might, for example, have zoomed into a space where you have 1/8 versus 2/8 or 1/4. And you can keep zooming in to the space between these. And I can always mark down the smaller fractions that account for points in between. But I can keep doing that forever and never getting to the end. So inevitably there's going to be some numbers within this number line that cannot be written as a fraction, and therefore in order to complete the number line we're going to have to include those, and these are called irrational numbers. So some common examples of irrational numbers are going to be numbers like pi, the exponential e, and a number like the square root of 2. So all the positive, negative integers, the rational and irrational numbers, all of these constitute a set which we call the real numbers. What I want to talk about now are some functions, and therefore what you can do with some of these scalars. And an important concept comes up in math called the fundamental theory of algebra, and it states that a polynomial of degree n has n roots. So let's talk about what that means. So a polynomial, that's a function that has degrees. It has various degrees of the powers of a given variable, and you sum them over. So you pick your coordinate system and your independent and dependent variables. So let's just pick y and x. X is independent, y is dependent. That's typical. And so we're going to write y as a function of x. And this function, in order to be a polynomial, can be a sum of x factors that could have varying powers of x. So a very simple example is x squared minus 1. So this would be an example of a polynomial. When you are asked to describe the degree of that polynomial, you're going to be looking at the highest value of the exponent in the expression. So since there's only one x term in this expression, and it has a power of 2, then this polynomial has the highest degree of 2. And what this theorem says is that if its highest power is degree 2, then it must also have 2 roots. Well, what are roots? Roots are the solutions to this equation if you set y equal to 0. So let's try that approach, and then we'll also look at it using a graphical method. So I'm going to set y equal to 0, and then I'm going to solve for x. So I'm going to add 1 to both sides. And then I'm going to take the square root of both sides. Now, every time I take the square root of something, you always get 2 solutions. You get a plus and a minus solution. So in other words, like the solution plus 1 or the solution minus 1. These are the solutions to this polynomial. They are the roots of this polynomial, or the zeros of the polynomial. All of those mean the same thing. Graphically, if we draw this out, if you want to see what this looks like, this polynomial is a quadratic, so it's a parabola, and its intercept is down 1. So it's going to look something like this. So where it crosses the x-axis are the locations of these roots. So this is plus 1, this is minus 1. So this theory of algebra states that if you know the highest power of your polynomial, then you also automatically know how many roots it must have. There's one example that seems a little strange. For instance, you can FOIL this out if you wanted to, but I'll keep that as this factor. If we try to solve this for x, set it equal to 0, and take the square root of both sides, and then you have 0 equals x minus 3, so x must equal 3. So you might think, well, that only has one solution. And really what this is a parabola that's being shifted over to the right um, to plus 3. So that's where the vertex of the parabola is. So it would be something like that. But in fact, what the theory of algebra would say about this example would be that you could break this function up into the two factors like this and set each of these up independently equal to 0. And so because both of those solutions result in the same answer, doesn't matter because you were able to get to each solution separately. So that's how the theory addresses that type of an example. We can look at one other one. Let's pick y equals x to the 4th minus 5x squared plus 4. So you ask yourself, what's the degree of that polynomial? Well, now there are a few terms that have x in it, but you look at the highest power. So this is degree 4 because of that 4 right there. So that means it has 4 roots. So what are the roots? Well, we're going to set this equal to 0 and solve for x. This is an easy example because you can actually factor this thing like you would a quadratic, except we can use x squared terms instead of x terms. So the factors of that get us 4 would be either 4 and 1 or 2 and 2. But to add up to get us -5, it would have to be -4 and -1. So now each of these separately will give us roots, specifically 2 roots each. So the roots are -2, -1, 1, and 2. So what does this function look like? It has an intercept at +4, so we know it has to cross here. But then it also has to cross at -2, -1, +1, +2. So it'll look something like this. Now I'm going to give you one other abstract example and take some time to think about what it means. So another polynomial, very similar to our first example, is x squared plus 1. How many roots should it have? According to the theory of algebra, it should have 2 roots. Okay, we'll solve it, set it equal to 0, and solve for x. So now before I take it any further, we're running into an issue. And that issue is this quantity right here. On our real number line, that quantity has not been defined. There are no real numbers that explain how much the square root of -1 is. This is implying that you can take two of the same numbers, multiply them together, and get a negative number. And there is no such number on the real number line. So we have very few options. We could either throw the fundamental theory of algebra away because it doesn't work in this case from what we can see, or we can figure out a way to make it work. And it became important for people, both mathematicians and physicists, to try to make this work, because equations that had these types of solutions came up pretty often. You'll see this a lot in engineering. And so in order to understand more about your system, you needed to come up with solutions that took this form. So there was people like Gauss, who is also very famous in physics for writing theories of electricity, came up with an idea of creating a new set of numbers that did not exist on the real number line, but were actually could be broken up into integers of the square root of 1. So this became our base unit of quantities along this new number line. So it'd be constructed along a new line. This line is completely independent of the real number line. The only place where they should intersect would be with the number 0, but otherwise each of these tick marks are increments of a square root of -1. So this would be the square root of -1 here. This would be 2 square roots of -1. This would be minus square root of -1. This would be minus 2 square root of -1. Having done that, let's go back to this problem here. After we take the square root of x squared, we get x equals, and we get two solutions, plus or minus the square root of -1, which means that we have x equals both plus square root of -1 and minus the square root of -1. So that means I can identify where they are on this number line. So that means this function must cross this axis here and here. So on one hand, you see that the fundamental theory works with the addition of this new set of numbers, because now we can say that the polynomial that has degree 2 has two solutions. The theory does not explicitly say that they should be real solutions as long as they are solutions. So these are not real numbers, but they are solutions nonetheless. So the problem is, where do they appear on the graph? If we graph what we would typically use as the x and y axis, x squared plus 1, that is a parabola that has been shifted up to have a vertex at plus 1. So again, this illustration, it helps us to make sense of the fact that this polynomial has no real solutions, because there is nowhere that it crosses this x-axis. But it somehow crosses the this other new axis. So one mathematician originally wanted to call these the lateral numbers because they just occupy a new dimension of numbers in this space. So if we have the y-axis and the x-axis as two independent real axes, then we could add a third axis that would be perpendicular to both x and y. So it almost behaves as like a z-axis that would come out of the screen into the screen. And that would be our new axis. So if we want to see what the function does along that axis, all we have to do is rotate our view 90 degrees. We would want, this is still an x-axis here, but this now is the real x-axis. So what do we call this? Well, lateral numbers didn't stick, and unfortunately the name that stuck keeps people from really appreciating how important these numbers are, and that name is imaginary. So this is the imaginary x-axis. So if we would have instead stuck with calling them lateral numbers, maybe some people would take them a little bit more seriously, but imaginary stuck. It's also that for that reason that people didn't want to keep writing the square root of -1, so they are we're now used to abbreviating the square root of -1 as I. So they mean the same thing. So this solution, for instance, can be written as I and -I. And to fill in the rest of these, you have I, 2I, -I, -2I. So if we spin this axis around, what would we see? You now have the imaginary axis here along with the y. Well, here's our two solutions are -I and I. But the function also has to cross the y-axis at +1. So you can test some other points, but you should be able to convince yourself that this is what it should look like. So there's this whole other shape to this function that was invisible to us because we weren't looking at it the right way. Try to do this in 3D. My drawing isn't that great, so I try to reproduce it in Algebra. So again, here's the x squared plus 1 with x in the positive, or the real x-axis and the y-axis. So now, if I can show you what it looks like in 3D space, where you have two real dimensions and one imaginary dimension, it looks something like this. Right? So there's your x squared plus 1, and we're just going to sort of think that this is invisible. You know, you can't see this space here. But now if I were to rotate it, you'd see this piece right here, and now this part becomes invisible. So that's the extra baggage that this function carries with it, is this other parabola, which is basically upside down, passing through points along an imaginary axis now. Okay? What I could also do with that view is tilt it so that the y-axis is facing out of the screen. And what that would do is give you two sets of axes that represent the x direction, but with two independent number lines. So typically, these would be the imaginary numbers, and this would be the real numbers. But they could both represent the same variable. This is the real x, that's the imaginary x. And you can actually create numbers that combine both real and imaginary numbers. Because remember, we can take a scalar and represent it with a dot. So I can place a dot here instead. We didn't have the option to represent dots that were not on a number line before. Now we can. So it can act almost like a point on an x and y axis, but it's just a number, just a single number, not a pair of numbers, but a single number. And so these create a whole new set of numbers, which are called complex numbers. The symbol that's used is C with a line going through it like that. And because technically it's like you have the X, Y, Z, so we're, looking for a new letter. A lot of times complex numbers are given the letter Z. So this is the complex number Z. And the way it can be written is as a combination of, just like you would sort of with coordinates, you could look at the real part and the imaginary part of this number. So let's say it's 4 units over on the real axis and 2 units up on the imaginary axis. Then the standard way of writing this number Z is 4 plus 2i. So in general, any complex number can be written as a real part and an imaginary part. So many solutions to very complicated equations can only be solved with using complex numbers. And this brings us into the next type of quantity that we're going to be focusing on, and those are vectors. And one way to think of a vector is in the same sort of way that it took us to construct this complex number. At this point, you may want to know where that number is in the plane. So what you can do is you can point to it. You can start from the origin and then draw an arrow that points to that number. And so what you've just done is created an object called a vector, because now this quantity here has both the length, which describes the distance that this number is away from the origin, but it also tells me some particular direction that is relevant in certain cases. The study of vectors is called vector analysis. And so all vectors can be represented with an arrow. What determines the uniqueness of that vector is how long the vector is and which way it's pointing. I can shift this arrow anywhere on the screen say, move it this way. But if these both have the same length and they're parallel, then they can be considered the same quantity. Just like, you know, one apple here is equal to one apple there. It doesn't matter where those apples are. One apple equals one apple. But if I either change the length of this vector or change its direction at all, then these become different quantities. Typically, the symbols that we use for vectors are boldface letters. So if you have the ability to write in boldface, you could do it that way. But the other way is using a little arrow on top of the letter. So the first thing you learn in vector analysis, just like you would with scalars back in first grade, second grade, is you want to add two numbers together. Okay, now with vectors, everything with vectors is just a little bit more detailed oriented. We can use the arrows themselves in picture form to add various vectors together, and that's called geometric addition. There are two methods that we can use to add two vectors together. One is called tip to tail method, and the other is called the parallelogram method. So we're going to try to add two vectors together with both methods. And at this point, it's just based on your preference on what you find to be easier. So I'm going to give you two vectors, and we're going to add them together. So this is our first vector. That's called vector A. So it's got that length, and it's pointing in that direction. And this is going to be vector B. So it's shorter, and it's pointing in a different direction than A. So we want to ask the question, what is A plus B? So to use the tip to tail method, I'm going to take the first vector in my setup, which was A, and I'm going to connect the tail end of B to the tip of A. So B goes off in this direction, it's a little bit shorter, and so that's B. A plus B is the vector that you get that connects the tail end of A to the tip of B. So we can call this vector now the vector A plus B, or we can condense it and give it a new letter like C. So we've just created a new vector. Notice that it does not have the length of A plus the length of B. It's somewhere in the middle. It is larger, so the length of C is larger than the length of A. It's larger than the length of B, but it's less than the lengths of A plus B combined. All right, important little fact for you to remember. Now, how do we do it using the parallelogram method? Well, the parallelogram method says to connect both vectors at their tails. So here's A, here's B. And what we're going to do is we're going to form a parallelogram. And so that basically means to just sort of shadow the b vector this way and the a vector this way. And that creates a parallelogram. And what we do is we cut the parallelogram along its diagonal. And so it would look something like this. And if we compare this vector c and this vector c, they should be identical. All right, they should have the same length and they should be pointing in the same direction. If you do it carefully, then these two vectors should be worked out to be the same length and direction. Because it doesn't matter which method you choose, you should get the same answer. So my next question is, do these vectors add together according to the commutative law? If you should remember what that means. That means, is this statement true, that a plus b is equal to b plus a? You would say that has to be true. But what I would ask you guys to do is, treat some things with a bit of skepticism, and because some things that you might have taken for granted when working with scalars don't necessarily work with vectors. But what we can do to prove that this statement is in fact true is by using a geometric form of addition and finding what b plus a would look like. So what I would do here is draw vector b first and attach to the tip of b the tail end of a. And in fact, we do get the same vector as we did here and here. So this law works. How do you subtract two vectors? Well, believe it or not, in order to know how to subtract, you actually have to first know how to multiply. Now, in this video, we're just going to talk about one form of multiplication, when in vector analysis there's actually three different ways of multiplying. So this is called scalar multiplication. That's when we take a scalar, and I'm going to call just our general scalar, the letter k, and multiply it to a vector like vector a. So what this does is it changes, first off, the length of the vector. So the length or magnitude, which is the proper term to use when we're working with vectors, of k times a is equal to the absolute value of k times whatever the length of a was. That is the new length of the new vector that's created by multiplying the scalar times the vector. So it is a new vector that we've created, so it also has a direction. The direction of Ka would be equal to the same as the direction of A if K is positive, and it would be opposite of A if K is negative. So let's try an example. So here's a vector that I'll call A, and what I want you to do is sketch what the following vectors look like. 2A, 0.5A, minus A, and minus 3A. So pause the video and try this on your own first and see if you get it right. Okay, so let's try 2A. So it's going to have a length that is twice what A originally was. And because it's positive, it's going to be pointing in the same direction. So 2A will look something like this. This new vector is half the size that A was. Also positive, so it's going to be pointing in the same direction as A. So it'll look something like this. This will have the same length as A, but because it's negative, it's going to be pointing in the opposite direction of A. So it'll look something like this. And then finally, this is 3 times the length of A, but pointing in the opposite direction. So it looks something like that. So what we've learned in using geometric addition, such as tip-to-tail method or parallelogram method, to add two vectors, and how to construct vectors by multiplying them with scalars, will ultimately tell us how to subtract two vectors. And it's based on the principle that A minus B can also be written as A plus negative B. So I know how to add vectors, so that means I can use tip-to-tail method. And so this is clearly adding two vectors together. I know what happens when I multiply a vector by a scalar, like -1. In this case, it doesn't change the length of B, but it flips it around so that it's pointing in the opposite direction. So if I want to add A plus negative B, which will ultimately get me what A minus B is, I just have to first flip B around so that it's pointing in the opposite direction, and then I can follow through with either tip-to-tail method or parallelogram method. I'll just do tip-to-tail for now. So I'm going to start out with A, and now I'm going to add to it negative B, which points it this way now. And notice, if you go back and see what our C vector looked like before, this is a completely new vector. It's going to have a different length, and it's going to be pointing in a different direction. And so this guy is pointing that way. So this new vector is A minus B. So we have to call it something like D. And that's how we subtract two vectors. The first thing that we're going to cover in class is setting up what are called unit vectors, and we're going to look at how to add, subtract, and multiply using unit vector notation, and it's going to be the type of notation that we're going to be using quite often from here on out when we're dealing especially in 3 dimensions. So look forward to seeing you all in class. Thanks for watching.